Okay, we're going to talk about section 3.3, how derivatives affect the shape of a graph. So here's the graph of a function. First, we need a little bit of vocabulary. So we can talk about different pieces of the graph having different properties. One of those properties is we can say part of the graph is increasing, or the function is increasing. That means the graph goes up and to the right in that section. And what that means in terms of the function is when x gets bigger, the function values, the outputs, will also get bigger. Other parts of the graph will be decreasing, down and to the right. And what that means is when x gets bigger, the function values or y values will get smaller. So I've shaded in a little part of the graph there in blue. That is an increasing piece of the graph. Then we get a little decreasing piece, which I've shaded in purple, and then an increasing piece again. So this one has two increasing sections and one decreasing section. To describe where the function is increasing and decreasing, we use x values. So I've shaded in the x-axis blue in where the x values on the graph would be increasing, and I've shaded in the x-axis purple in that decreasing section. We need a few labels on our x-axis, so there's x values a and b there. And we would say that this function is increasing on the intervals -infinity up to a and b up to infinity. We would say the graph is decreasing, or the function is decreasing, on the interval from a to b. Now, I don't care whether you include endpoints or not in this, but WebAssign will care. So increasing and decreasing intervals, you should use square brackets, include the endpoints, except for infinity and -infinity. You never include those guys. Well, what does it mean to be increasing? Well, it means that you're pointing up and to the right, which means your tangent lines, which I've drawn a little bit there, also point up and to the right. And a line pointing up and to the right has a positive slope. So increasing parts of the function, the tangent line slopes are positive, and that means the derivative is positive. So increasing parts of the function have positive derivatives. Similarly, decreasing parts of the function have tangent lines with negative slope, and that means the derivative is negative. So decreasing parts of the function have negative derivative. Notice that there's a local maximum here at x equals a. The highest point in the vicinity is at x equals a, and that happens because the graph has been increasing but then starts to decrease. So the highest it gets in that area is at x equals a. So local maximum occurs when the graph switches from increasing to decreasing, or positive derivative to negative derivative. In the same way, we have a local minimum here at x equals b, and that happens when the graph switches from decreasing to increasing. Okay, here's our same function again, same graph, but now I want to talk about something different rather than increasing and decreasing, and that's sort of the way the graph is curving. If I draw a whole bunch of tangent lines, here I've drawn tangent lines at lots of points on the graph, you can see that there's some parts of the graph where the black function graph is above the tangent lines, the red tangent lines, and there's some places where the black graph is below the red tangent lines. We have names for these two properties. We call the function concave up when it is lying above the tangent lines, and we call the function concave down when it is lying below the tangent lines. So you can see there's two sections of graph here that are above the tangent lines, and I've shaded those in purple. Those are concave up. And there's two sections of graph where the graph is below the tangent lines. Those are in brown. That's concave down. There's A and B from before. A is where there's a local maximum, and B is where there's a local minimum. But now we also have a few other x values that are important, C, D, and E, where the concavity of the graph switches. It switches from concave up to concave down, or concave down to concave up. Just like before, we talk about intervals. So this graph is concave up on the interval from -infinity to c, and also on the interval from d to e. And the graph is concave down on the interval from c to d, and the interval from e to positive infinity. unlike with increasing, decreasing, we use parentheses instead of square brackets here, so we don't include the endpoints for concave up and concave down. Again, I don't really care. On a test it won't matter, but for entering answers in WebAssign you may need to know that. Okay, concave up sections, if you look, the slopes are getting bigger. That means f prime, the first derivative of the function, is increasing because f prime gives you slope. So f prime is increasing, and we just on the last slide said that increasing functions have positive derivatives. So that would mean the derivative of f prime should be positive. In other words, the second derivative of f should be positive in the places where the function is concave up. Likewise, in the concave down areas, the slope is decreasing. That means the derivative f prime is decreasing, and that means the second derivative is negative in the areas where the graph is concave down. There's also words for places where concavity switches. Those are called inflection points. This graph has 3 inflection points at x equals c, x equals d, and x equals e. Notice we now have 4 basic ways to describe pieces of graphs. A piece of a graph can be increasing and concave up, which looks like this. It can be increasing and concave down, which looks like that. Decreasing and concave up looks like this. And decreasing and concave down looks like that. You should sort of get familiar with that so that if you know you want to draw something increasing and concave down, you won't have to think too hard about what it should look like. In general, you need to be very familiar, very comfortable with all these terms. Increasing, decreasing, local minimum, local maximum, concave up, concave down, inflection point, right? Know what those mean. Know what those mean in terms of what the graph would look like if it's got an inflection point, or if it's got a local minimum, or if it's decreasing, or if it's concave up, etc. But also know what those terms are in relationship to first and second derivatives. For example, you need to know that a local minimum is where the first derivative switches from negative to positive, or concave down means the second derivative will be negative, things like that. For the video quiz in class, you will need to know all those terms and be able to draw curves that have those properties, be able to tell me how they relate to derivatives. I will see you there.